There's a problem with Earth's core. It's right here under our feet, but we've never actually seen it. Today, we're going to fix that. We're going to find a solution to drill all the way to the center of Earth. And then we'll see you fall right through the planet. This is going to be fun. Or not. Okay, let's open Earth up. Before going all the way to the core, you need to drill through the crust. Now, humans have attempted to drill through Earth's crust before, but as we went deeper and deeper, we had to shut that down and seal it off. We didn't even get that deep. Yeah, this is the Kola Superdeep Borehole. It's deeper than the Mariana Trench. It's the deepest place on Earth. Scientists started drilling it in the 1970s, and over the course of 2 decades, they went through unexpectedly extreme temperatures, deep granite oozing like hot plastic, and snapping drill bits. And in 1989, the project was shut down. The Kola Superdeep Borehole is 12.3 kilometers deep. That's 7.6 miles. It's significant, but compared to the Earth's radius of 6,378 kilometers, it's barely scratching the surface. To get all the way to the core, you'd have to drill a lot deeper. Specifically, you'd need to drill 6,378 kilometers deep to reach the center of the planet, and then another 6,378 kilometers if you wanted to dig a hole through the entire Earth and get out the other side. But let's start with the crust. The crust is the very top layer, and it's not very deep. Under the continents, it stretches between 40 and 70 kilometers, and it's mostly composed of lighter rocks like granite. Now, under Earth's oceans, that crust is only about 5 kilometers thick, but it's denser basalt rock. Now, choosing the right place to drill would be the first and most important step in your digging journey. If you started drilling your hole anywhere near the equator, well, you couldn't fall through it. That's because Earth's rotation would become a problem. Yeah, this is what scientists call the Coriolis effect. Even though Earth makes one full rotation every 24 hours, not everyone on the planet is moving at the same speed. It all depends on how far you are from the poles. At the equator, the surface and you are rotating eastward at about 1,600 kilometers per hour. It's 1,000 miles per hour. You could drill a straight hole at the equator, but you couldn't fall through it. Because of the Coriolis effect, you'd be slammed into the eastern wall of the tunnel almost immediately. Now, to save yourself from slamming into a wall, the tunnel would need to be a complex, mathematically precise curve. That's too much math for me. Now, at the poles, which are Earth's axes, there's barely any sideways rotation. Here, you could drill straight down. But which pole would you choose? The South Pole is on the continent of Antarctica, and the crust here is extremely thick, between 30 and 40 kilometers deep. The North Pole is right in the middle of the Arctic Ocean, and it sits directly over the Gackel Ridge. This oceanic crust is much denser than the continental crust, but it's thin. Here, tectonic plates are pulling apart so slowly that Earth's crust is less than 4 kilometers thick in some spots. So, by starting in the Arctic Ocean, you'd hit the Earth's mantle almost immediately. But you'd have to drill underwater, and that would make things difficult for you. Now, you'd also have to consider that this project would be costly. But I might just have a brilliant solution for you. Start digging here, in the Mid-Cauca Belt in Colombia. Why? Well, because this is the place where you would find gold on the way. A lot of gold. Okay, most of the gold on our planet arrived from the stars back when the asteroids slammed into Earth billions of years ago. And then all that gold quickly sank into the core. But you don't have to drill all the way to the center to find it. Some of this precious metal is right there, close to the surface. That's because deep in the mantle, tectonic plates collide, creating massive amounts of heat and pressure. Well, this forces gold-rich fluids to move from the core to the crust through volcanic eruptions. As these fluids climb closer to the surface, they hit a point where the pressure drops so suddenly that the liquid gold flash freezes into solid rock. There are a few geological areas around the world renowned for massive gold discovery, including the Witwatersrand Basin, South Africa, the Abitibi Greenstone Belt in Canada, Carlin Trent in Nevada, USA, and Colombia's Mid-Cauca Porphyry Belt. Colombia is a geological titan, home to superdeposits like Alpala, La Colosa, Buratica, Nuevo Chakiro, and the Marmato Mine. Together, Colombia has produced over 100 million ounces of gold this century, and it remains one of the most underdeveloped gold-producing regions on Earth. This is exactly where Tiger Gold, TIGR, on the TSX Venture Exchange is operating. They work at the edge of what's physically possible. At their Quinchilla project, they aren't just looking at one deposit, they're studying 4 major ones: Miraflores, Tesorito, Ceibal, Chuscal, and what's unusual about these deposits is that they sit very close together. Tiger Gold is using predictive mapping to trace these 4 deposits back toward their deep origins. Their geological models suggest that these sites may be vertically connected to a single massive mineralized system deep underground. The system that hasn't been fully tested until now. While you've been hypothetically drilling to the center of the Earth, Tiger Gold has spent the last year unlocking over 2 million ounces of gold, all in the real world. And they aren't stopping there. Tiger Gold has launched a massive 20,000 meter drill program to unlock even more gold beneath the surface. Instead of randomly digging for gold in hopes to find some, well, they have a number of known areas where gold has already been found. And they're drilling and they're using predictive feeder zone mapping to trace gold back towards its deeper origins. In 2026, the global economy might feel as volatile as a shifting tectonic plate, but gold remains the ultimate insurance policy. If you want to see how Tiger Gold is de-risking the journey toward the next major discovery, well, head on over to tigergoldco.com to follow the mission. As the global economy grows more uncertain, gold remains the ultimate product of extreme planetary forces. And Tiger Gold, TIGR on the TSX Venture, is on the verge of a potential major geological discovery. If you want to see how Tiger Gold is uncovering the secrets of the Mid-Cauca Belt, head over to tigergoldco.com to learn more. Okay, now it's your turn to drill. This ambitious drilling project would take a long time. I mean, the Kola super borehole at 12 kilometers deep took scientists 24 years to drill. So, on average, they drilled about half a kilometer per year. Now, if you found a solution to the melting equipment problem and kept drilling to the core at the same pace, it would take you 24,984 years to get to the center. If you wanted to have this hole all done today, you'd have to have started this project during the last ice age, when mammoths were walking around. And you'd have to approach every one of Earth's layers in a different way. For starters, the crust. Colombia's Mid-Cauca Belt sits on a crust that's about 45 kilometers deep, so you'd have a lot of work to do. Now, for the first few kilometers, you'd use conventional rotary drilling with diamond bits. Yeah, I mentioned this was going to be costly. That's exactly why you'd be going through the gold-rich rock first. But as you went deeper, the rock would get so hot, it would be like drilling into hot, squishy plastic. German scientists once drilled a hole 9.1 kilometers deep, and they clocked the temperature 265 degrees Celsius. That's over 500 degrees Fahrenheit. Drilling in Colombia would get even hotter. And at the very bottom, the crust could be as hot as 1,000 degrees Celsius. Yeah, any mechanical drill would become useless. You'd have to switch to millimeter wave directed energy drilling. This is a kind of super-powered heat laser. A surface machine called a gyrotron would send waves down a metal tube through the crust. There, it would heat up the rock so much, it would practically vaporize. If you blasted this laser into the crust 24/7, well, it would take you 1 year to get to the bottom. The next stop is the mantle, specifically the Upper Mantle. The Upper Mantle stretches from 45 kilometers to 670 kilometers deep. It's mostly made up of rock called peridotite, but it's very, very hot, around 1,500 degrees Celsius. You'd need an extreme heat-resistant suit to go down there. And of course, you'd keep using your laser to cut through this rock. But here's the problem. This intense temperature down here turns rock into thick peanut butter. You ever try poking a hole in peanut butter? It doesn't stay as a hole, does it? It closes. So your hole to the center of Earth would keep closing as you were beaming it. The only way around that would be to somehow crystallize the walls of your tunnel to the planet's center as you drilled. It would be a long and difficult process, and we don't even have the technology to do this right now. But if you somehow kept drilling at the same pace you drilled through the crust, it would take you 14 years and 4 months to get all the way down to the Lower Mantle. Yeah, you worked so hard and so long, and you still didn't even drill through the whole mantle. Now, the Lower Mantle is unimaginably extreme. At this point, you'd be drilling through deep earth, fighting through crushing pressure over 1.3 million times stronger than on Earth's surface, and soaring temperatures of 3,700 degrees. That's 6,600 degrees Fahrenheit. The heat radiating from the walls would be enough to incinerate any material. If you were planning to get this deep into Earth, you'd need advanced active cooling. And you guessed it, we don't have that kind of tech right now. The Lower Mantle is very thick. It stretches from 670 kilometers to 2,890 kilometers deep. If you could even keep up with the speed you've been drilling earlier, well, it would take you more than 50 years to get through this incredibly hot and thick layer. Finally, after 66 years of non-stop drilling into the planet, you'd get to the outer core. You're not at the core yet, but you'd be close. Here, everything would change. You'd no longer be in solid rock. The outer core is an unimaginably vast, turbulent ocean of soupy liquid iron and nickel. The temperatures here are so extreme, they're in the same range as the surface of the sun. Yeah, if you thought the mantle was hot, well, the outer core is between 4,500 and 6,000 degrees Celsius. I have no idea how you could survive here. This kind of temperature and all that pressure would incinerate and crush you within milliseconds. And if you did survive, well, drilling here would be impossible. You just can't drill through a liquid. You'd have to sink a physical, indestructible pipe through the molten metal to keep your tunnel open. And you'd be sinking 2,260 kilometers of piping into a swirling liquid iron ocean. But here's the good news. Instead of mechanically pushing it down, you could just let gravity do the work. If your pipe was made of an ultra-dense material that's heavier than the surrounding liquid iron, well, it would sink under its own weight. And it would sink fast. That's because the liquid iron in the outer core has a consistency similar to water, even though it's over 10 times denser. So it wouldn't create much resistance for the pipe. It would take you a little over 5 days to push the pipe down. Now, the outer core is what generates Earth's magnetic field. Yeah, all that molten iron moves around because of extreme heat and the planet's rotation. Because this liquid metal conducts electricity, all that swirling creates a Geo-Dynamo effect. It's like a massive natural generator. It generates the electric currents that power our magnetic field. And because of all that, the magnetic forces here would be 50 times stronger than you experience at the surface. Your navigation equipment and electronics would be useless at this point. You'd be drilling blinded by Earth's magnetism. But like I said, it would take you a few days to sink through the entire outer core. And finally, you'd reach your destination. Well, almost. Earth's inner core stretches from 5,150 kilometers to 6,370 kilometers. You wouldn't be at the center of Earth yet, but you'd be close. The pressure here would be 3.6 million times higher than the pressure at sea level, and the temperatures would be hotter than the surface of the sun, up to 6,000 degrees Celsius. That's over 10,000 degrees Fahrenheit. Now, you'd think it would be another layer of metallic soup, but no. The core is dense, all because the incredible pressure is keeping it solid. You'd re-engage your laser beam. Hopefully you took that thing with you through the outer core. Now, there would only be about 1,220 kilometers between you and the center of the planet. With your laser drill, it would take you just under 28 years to get there. But finally, you'd be standing at the very source of the force that keeps your feet on the ground, right at the center of the planet. But you'd feel absolutely nothing. Now, we think of gravity as a downward force, but down just means toward the center of mass. As you drill toward the core, more and more of Earth's mass would actually be above you. Once you were in the center of Earth, inside a solid sphere, the mass of the planet above your head would cancel itself out. The gravity from the bits of Earth to your left would be canceled out by the bits of Earth to your right, and the stuff above you would pull you up just enough to negate some of the pull from the core below. By the time you reach the exact center, you'd be in the middle of a global tug-of-war where every side is perfectly matched. You would just drift in the middle of it, just like an astronaut on the International Space Station. Every atom of the Earth would be pulling on you, but because they'd be pulling in every possible direction at once, the net force would be zero. Now, to get to the other side, you'd have to repeat the entire process in reverse. From the center, you'd have to drill through another 1,220 kilometers of solid inner core. Now, since you'd be working against gravity, even though it's weak at first, it would feel like a constant uphill climb. Then you'd blast through the 2,840 kilometers of mantle and the final thin layer of crust. Now, if you kept your laser drill running at the same record-breaking speed, well, the entire return trip from center to the surface would take another 90 to 100 years. Okay, so your megatunnel is finally finished. It goes from Columbia straight through the core all the way to the other side of the planet. And now is the time to send you through it. You put on a heavily shielded spacesuit, pump all the air out of the shaft so that the air resistance doesn't burn you up, and then you jump. At first, it would feel like regular skydiving, only you'd keep accelerating because there would be no air to slow you down. Your speed would keep climbing. By the time you hit the mantle, you'd be moving at insane speeds. Exactly 21 minutes after the jump, you'd blow past the center of the Earth at 8 kilometers per second. That's about as fast as the International Space Station zips around Earth. You'd blast through the zero-gravity core at maximum speed, and now you're heading up the other side of the planet. Gravity would be pulling against you now, and it would slow you down. But your massive momentum would carry you all the way out through the outer core, the mantle, and the crust to the opposite side. Exactly 42 minutes after you jumped, you'd pop out the other end of the hole. Your speed would hit 0 for a split second at the surface. You'd be right in the middle of the Indian Ocean, near Indonesia. Now, if you didn't grab onto the ledge at the exact second you reached the surface, gravity would pull you right back down. You'd fall back toward the core. You'd be falling back and forth inside of Earth forever. Yeah, you probably shouldn't have jumped here, but it's too late. You're stuck. Next time, why don't you try jumping somewhere where you could enjoy the view? Like in the Lake of Titan. But that's a story for another What If.